we continue on the topic of collective motion. João is going to give a talk about that.
Can you hear me? Can you all hear me? Yes. Is it working? Yeah, cool, cool. Thank you. Okay. So during the next 25 minutes or so, I'll talk about Swarmalators, okay? And I know that the name sounds weird. It's not related with epilepsy or something like that. It's actually related to the Kuramoto model, kind of. But since I know it's kind of strange for most of you, what I'll show you is how to build a model from something very, very simple. Then I will show you a couple of examples and a kind of two-dimensional system, but that's the idea, okay? So a couple of years ago, I would have started showing this example of the fireflies, because that was cool. That was standard, but there is some controversy now. And I'm very happy that no one showed this example. Okay, so this is a very clear example of synchronization. Okay, it doesn't, wait. Can you hear it? Does it work? Okay. So the idea is that you have a group of people, and they start clapping at a certain manner, and then after a transient that is very, very sudden, they start clapping in unison, okay? They synchronize, right? So this is a clear example of synchronization, but if we want to model this, we need to make several things. I mean, you have people, you have many types of interactions. It's very hard. It's very complex, okay? But, if we try to simplify this, we can think that each of these individuals is a limit cycle oscillator, okay? So that's an oversimplification, but anyway. So you have the limit cycle oscillator, and we can make another assumption, okay? So we can say that there is a variable that travels along this limit cycle, right? And we call this variable phase. So after a couple of additional steps, we can find the dynamics of this phase. Okay, that's called phase reduction technique. That's not the focus of this talk, but it's important to know it. Once we are on this phase space framework, we can talk about the Kuramoto model. The Kuramoto model. And the Kuramoto model is based on that. Okay, so when we are in this framework, we say that each individual is described by internal phase. Okay, the phase is given by this theta. And if we isolate an individual, it will keep oscillating. Okay, that's because we have this omega. That's the intrinsic frequency. But we know that these individuals are connected, right? There is some interaction. That's why we have this interaction term that is very simple, and it's based on the phase difference and a coupling strength. That's it. Okay, so the model is very simple. I know you have seen this during the week, but I'll do an additional assumption, and I'll say that these individuals are identical. And if we do that, we can change the rotating frame, and we can get rid of this guy. So in the end, we get this. So this is even simpler, right? And without technicalities, we can understand the behavior of the system from this equation, okay? Now, since we have phases, and these phases are periodic, we can position these phases on a circle, like this. So I have my focal individual, this guy here, with two neighbors, right? And according to the equation, the contribution of the neighbors depends on the phase difference, okay? So if the neighbors are very close, and the phase difference is about 0, the contribution is 0. But if they are far, there is a contribution. And what this contribution generates is basically that these guys will chase each other, okay? They will be trying to follow each other, and in the end, the result of that will be this state. And this is synchronization, okay? In this case. Now, you can use this equality on the equation, and you will see that the result is 0, meaning that that's an equilibrium state. And that also means that once these guys reach this point of synchronization, they will stay there forever. So that's what we call a static state, okay? So that will be important in a few slides, but that's the idea. Now, we are talking about synchronization, but we can also have asynchronization, okay? If our coupling strength is positive, we have synchronization. If not, it's asynchronization. Okay, so we have only two states. That's it. Now let's think about two variables. We have our phase, but we also have an additional variable that we call position. Okay, so we have the position dynamics that is basically the same, right? That's also periodic, and we can couple these two variables using a cosine function. So you can see now that the positions affect the phase dynamics here, and we also have the phases affecting the position dynamics, right? What's the effect of this new function? We can make the same exercise we did before with the Kuramoto model, and now we will position these individuals in space. Since we are talking about a position in this x variable, we are talking about a periodic space, right? It's a ring, it's a physical ring. So now we have, again, our focal individual xi and its neighbors, and we know from the previous example that the effect of this sign is that of the guys converging to a specific position, right? That's what we know from the sign. Now we have to define the phases, okay? And since I'm using the positions in the circle to define the positions, I'll use colors to define the phases, okay? So for instance, the two guys in blue have the same phase and different than the guy in red. It looks like red. So since these two guys in blue have the same phase, the difference will be 0, and the effect of the cosine will be maximum. If it's different, it will be less than that, right? But in the end, it's just a scaling, okay? It's just a scaling factor. So in this case, for instance, this attraction will be higher or stronger according to the similarities in the phase. But that's it. So in the end, the effect is very similar. It's very, very similar. So we can expect to have the same states, right? We had sync and async. And since this is behaving very, very similar to the Kuramoto model, we can say, well, we should have sync state, like this one. You can see that we have the convergence to 2 points in space, right? All the individuals, we have started this simulation with a number of individuals, like 500. And after a transit, they reach these 2 points, okay? And all the guys in one cluster have the same color, same with the other cluster. Now, we have 2 clusters because of the cosine, okay? Because cosine of pi is 0, and basically, when they are separated by pi, there is no interaction, there is no effect, okay? So we had synchronous state, we had the asynchronous state. So we also have asynchronous state, okay? Remember that the colors are the phases, and the positions are like distributed on the ring. But in this case, there is something additional, and it's because of these interactions. Actually, we can define these new variables, these xi and eta, and we can derive new equations, and we could get a Kuramoto equation of correlations. And that's why we have this additional state that is called phase wave state, okay? And it's basically a state of correlations, okay? That's why we have this nice pattern. So now we have 3 states. We have sync, async, and phase wave. The thing is that, you know, these states are static, right? These particles converge to these positions, to these phases, and that's it. They remain there forever. But we don't like the static because, you know, many systems in nature are active. So individuals move and everything. So we wanted to recover that. And the first thing we could do is to consider that we don't have identical individuals, right? That will mean that we have an omega at the beginning of this equation, and that generates some motion. But that's hard. I mean, if you see the literature in the Kuramoto model, you know that makes things a little more tricky. So you have to apply different things, and to keep it simple, we opted for a second option. And that option is considering a phase frustration, okay, a delay. So you can think about the synchronous state. We have these guys, this equality, theta I equal to theta j. And if you plug that to the sine function, you won't get this equilibrium state being equal to 0, right? You will have this sine of alpha. So there is an effect, and that generates a motion. Okay, so we get the motion that we want in a different way, but this is still simple. We can still handle this equation analytically. So considering this delay, we can think about our states, and we can say that if for the Kuramoto model, we had 2 states, and using 2 variables, we have 3 states, if we add this phase frustration, we should get motion also in our spatial degree of freedom, right? So we are adding frustration here, and you can see that it's symmetric. We have alpha affecting the positions, and we have beta affecting the phases. And we had sync, async, and phase wave. So now we have active sync, and you can see that they rotate, which is what we wanted, and they're also changing colors. And it's periodic. I don't know if you can see it, but they are changing colors. Okay, our second state was the asynchronous state, right? Now we have active async. Again, we have this distribution, this incoherence, but they move. And the third state was the phase wave state, and now we have the active phase wave state, okay? Cool? So far, so good. Now, since we know these states, we can describe these states. We can write expression for these states, and we can perform a linear stability analysis from that. And I'll show you the results of that. And the idea is that we want to know where in the parameter space these states are stable, where these states will emerge, basically. So before I show you this space, I have to let you know that these are the colors I'm using. I don't know. Okay. These are the colors I'm using for these states. And you will see this gamma plus, gamma minus instead of alpha and beta, because that makes everything easier. So the first case, it's the easiest one, where the coupling strengths are 1, both. And you can see that the shapes are trivial. These structures are trivial. So for instance, we have in the middle, here in the middle in this box, we have the synchronous state. We will have correlated states here, here, and here, and here, and so on. That's easy, okay? Something interesting here is that if we consider the model without this phase frustration, we cannot get the states with all these states with J1, K1, right? We have to change this coupling strengths to get all these states. But in this case, we can fix J and K, and we will still get all these states, okay? And that's because of this phase frustration, basically. Now, if we make K a little smaller, we get something like this. And you can see that it's getting interesting, right? So we now have this shape here, and this shape here, and those are regions of B-stability. And if we make it even smaller, we get something like this. Okay, so these structures are not trivial. For instance, this guy in the middle, that looks like a circle, it's not a circle. Okay, so it's interesting because, for instance, in these regions, we have multi-stability. It's not just B-stability. Okay, we can have 3 states there. So still, this is like the simplest case because we can make K negative. And when K is negative, there is something interesting, that we also have blank spaces. You can see, for instance, here, a blank space. And these red circles and stars and squares represent new states, disordered states. Okay, and I'll show you a couple of these states. First, we will start with a turbulent state. And the turbulent state is positioned here. So it's very close to the synchronous state. So you might expect to have like 2 clusters or something like that. But it's not. It's actually a state with disorder. And you cannot really see 2 clusters. Okay, and you can see actually that some particles are moving to the right, to the left. But we didn't call this state turbulent because of this, but because of this. So what I'm showing you here is the state of each individual in the x and theta coordinates. And you can see that they are forming structures that look like vortices, right? And something interesting is that in the middle of these vortices, you can see point clusters of individuals, meaning that there is coherence in phase and space. There is synchronization. And these synchronized points are surrounded by clouds of incoherence, okay? So yeah, it's like a chimeric behavior, basically. Good. The next state is the ring state, and it's not in one of the blank spaces, but it's very close, or it's in the boundary of the synchronous state. So again, you can expect to have two clusters, and we actually get two clusters, but they look weird, right? They move, and they have this space. And we didn't call these ring states again because of this, but because of this. Okay, so it looks like we had the synchronous state, and as we approached the boundary, it started to explode, but it didn't finish. So this is very interesting. These are not the only states that we found. We have more, but I have to go to the second part. Okay, so some partial remarks, basically, that I try to show you how to build a very rich model from something very, very simple, that is probably the simplest instance of the Kuramoto model. And we went from two states, synchronous and asynchronous, to many more. That's one thing. Second thing is that we use the Kuramoto-Sakaguchi model as an inspiration to create this new model. It's just basically considering an additional variable, the phase delay. And finally, I haven't mentioned this in purpose, but you have probably realized already that the name Swarmalators comes from two words. We have the swarm from swarming, and we have the lators from oscillators, because the oscillators sync and the swarm swarm, right? So we have sync and swarm, okay? But it's hard to see the sync and swarm in this case because we are in one dimension. We are moving along this ring. And we don't have these original features of the swarming where particles repel each other, right? They are all attracting here. So that's a problem. And we wanted to solve that. And we started playing with 2 dimensions, okay? So we have a very first try, and it's a very naive way to model it. And we base this model on this one-dimensional model, but we now consider a second dimension, a second spatial dimension. Okay, so we have the x now. Where is it? The x now. We have y, which is basically the same. And now the phases consider effects of the differences in x, differences in y, right? But that's it. There is not much change. It's basically the same, you see? So if it's basically the same, we should expect very similar states, right? We had, for instance, our coherent states were sync, async, and phase wave, okay? So we are expecting that. And something I have to tell you before showing you the states is that since we have now x and y, we are not talking about a ring anymore, but about a torus, okay? So we have the space is periodic in x and y. That's why it looks like this. I won't show you the space like this. I will show you the space like this, which is also periodic. It goes from minus pi to pi, minus pi to pi. And okay, so the states are this, okay? And here is not like much surprise because it's basically the same. We are just considering an additional variable, right? So we have the synchronous state, which is the same. We have an async state. We have a phase wave state. And we have this thick phase wave state, which is based on the distribution between x and y. Right? We have phase wave state in x, phase wave state in y, and we get that. But that's it. And there is a big problem here related with the swarming that we are considering or full attraction or full repulsion. We don't have like a difference between attraction and repulsion. If we consider that J is positive, it's attraction, and if we consider that J is negative, it's full repulsion, okay? And that's all good because we have the particles overlapping. So we have a second model. And in this second model, it's a little more complicated, but we consider attraction and repulsion, okay? I won't get into much detail, but the idea is that these guys are differences, okay? So that's xj minus xi. So in general, we are still using this idea from Kuramoto of using the phase differences. And considering this, we can get similar states, but in this case, since we have this repulsion part, we don't have overlapping. It looks like there is overlapping, but there is no overlapping, okay? So we have the point sync, the synchronous state that we know, but we also have a distributed synchronous state, which is this one. It's synchronous because they all have the same color, right? It's the same phase. We have the same with the asynchronous state. We have the phase wave state, like this. Since we have 3 variables, we can have correlations between x, y, and x, y, and theta, basically. So for instance, here we have positive correlation between x and y and x and theta. In this case, we have negative correlation between x and y and x and theta. But that's the idea. So again, since we know these states, these are coherent states, we can use this linear stability analysis. And again, I'll show you this parameter space. But in this case, I'm using different colors. Okay, so you will see, again, multi-stability. But in this case, the ones who are sharing this color, for instance, are multi-stable regions. That's the idea. Okay, so the regions look like this. And it's nice. I mean, we have like kind of trivial structures, but there is something additional here. We have this region. These are not mentioned on this table. These are not listed, basically. And there is a reason, and I'll show you now. Let's see if it works. Yeah, so I'll show you now first the state that shows up here in the middle. Okay, this is the distribution in x, y, and theta. Do you see something familiar here? Remember that we have periodic boundary conditions. Okay, so the real behavior is having these two kind of wings connected in the middle, and they are sharing particles and everything. Okay, so wings. So yeah, this looked interesting. And if we plot the behavior of a single individual on the torus, it looks like this. Okay, and if we plot the behavior of more than one individual on the torus, they all converge to something similar. So this looks like a chaotic behavior. Okay, so that was why we evaluated chaos, and these are actually chaotic states. Okay, so we have chaos here, chaos here, and chaos here. And it goes from this phase wave state to chaos. So I'll show you an additional state now. And this state is positioned right here. Yeah. So what is interesting here is that you don't see these wings anymore. It's disorder. And it's interesting because in the previous case, there was still correlation between x and y. In this case, there is no correlation at all. And if you see the trajectory on the torus, it looks like this. So it's crazy. Now, remember that we have 3 n dimensions, n being the number of individuals, right? We don't have 3 dimensions, actually. So this is kind of a projection, okay? But these are chaotic states. We evaluated that. So to finish, yeah. Well, I have shown you how to build a model from scratch, basically, from something very, very simple. And we try to keep this simplicity based on the Kuramoto model. Okay, and the pros is basically that we can solve it. We can find these states where, we can find the regions where these states merge. That's something that you cannot usually do in swarming models, for instance. Another thing is that we have two-way interactions. It's not like we have phases affecting the positions or the positions affecting the phases independently. We have both type of affections. Positions affect phases, and phases affect positions. And finally, since this model is based on the Kuramoto model, yeah, you have many things to do, right? You can add, I don't know, higher-order interactions, forcing, stuff like that. So yeah, this is I'll say a new type of system, interesting system, and that's it. If you like to see more details, you can check these papers. And of course, Marcus is the main collaborator because he's my advisor. And you can access the papers easily taking a picture of this code. And that's it. Thank you. Yeah.
Thank you. Okay, thanks, João. Questions? Yeah.
Thank you, Marco. Oh, thank you, Joan. Very interesting talk. I have a question that may go into another question. The point is about the first model, the ring, the one, what you call the one dimension. It's difficult to say what kind of physics that is, because the X are, if they are, to have the sync, they have to be together well. But that's just another problem. My problem is that if X represents a special variable, then there is a problem, at least in the drawings that you have shown, because then they cannot cross each other. I mean, once you start, they cannot cross each other. They are all of them on the ring. So they're all of them. It's a different thing with the faces. But if the X represents, let's say, a ball, give it like that, and you have 2 or 3 balls, one cannot pass the other.
Why?
One simply cannot pass the other, because that was precisely what led the people to believe that there were no phase transitions in one dimension, because one couldn't cross the other. So that is the thing. So what I'm thinking is that the first model, the one that you call the ring, represents a torus. In that case, there is no problem of crossing. Sorry?
Yeah, it's a torus, but yeah.
Well, it may even be a thin torus, but it's not a real particle going around the ring.
Yeah.
Okay?
Yeah, sure. Yeah, you're right.
That's what I think.
Yeah, you have to think about putting fireflies on a tube
Yeah.
that they go around.
Yeah.
But you're
Yeah,
right.
you're right, right.
Yeah. Thank you. Any other questions? Yeah.
Thank you for the nice talk. Please, I have maybe 1 or 2 quick questions. The first one is about the model. In the 1D and the 2D part, it seems like you use a complete graph to encode the topology of the networks. But we know that Swarmalator have a lot of application in robotics. So in the case of robotics, for example, if I want to reproduce exactly the same behavior that you mentioned here, for example, I think we will have one problem. One problem that we will have is the threshold distance in terms of sensor, for example. Do you think that your model will still work in this case?
Oh, that's a good question, actually, because the thing is that since we are using these like periodic variables, the way we did it was basically we avoided trying to handle the distance, the Euclidean distance. So we cannot describe a radius of action, you know? Yeah, you can do that if you consider the distance. We don't consider distance. Yeah, I mean the Euclidean distance between individual and individual. Yeah.
Okay, thank you. The second question is just a naive question. It's about the model also. So in the 2D model, the X and Y are the position, right?
Yeah.
But 2 equations are exactly the same.
Yeah.
Why?
Yeah, I mean, that's why I say that it was a first try. It works, but it was just to see that you can have patterns in a flat space, kind of. I mean, in the torus. Yeah, that's it.
And do you think it's possible in some real situation to have maybe some point in the space and the X and the Y position are exactly the same?
Yeah, in that case, it's possible.
No,
Yeah.
in a real situation.
Yeah. What's that?
In a real situation, it could be possible?
In that situation where X and Y have the same dynamics, it's possible because you are not defining repulsion, basically. They can attract, they can overlap each other. Yeah.
Okay, so we can continue after. Thank you.
Very nice talk. I'm interested in the phase wave conditions. Have you tried to see if the phase wave persists dependent of the number of the elements?
Yeah,
And considering if you do not have a full, like I said, all-to-all connection, this phase wave still persists?
Yeah, it persists. Yeah.
with a lower number and without all-to-all connection.
What's that?
If you remove the all-to-all connection, then
Oh, if we remove the all-to-all connections.
Yes.
Oh yeah, no, I don't know if it will. I mean, I don't think it will like be there still. Yeah. We have worked all-to-all in all the models basically. Yeah. No, that's actually the problem, because there is this model where they consider the distance, but it's analytically intractable. That's actually the reason why we have been trying to make models using phase differences and periodic boundary conditions. Yeah, because when you use the distance, it's impossible. Yeah, it's very hard. You can get very nice states, but besides that, you cannot treat it analytically. Yeah.
Maybe very quickly, because you said nice states, and now I'm curious. Did you get something like periodic Turing-like patterns of this, when you have, for example,
No, yeah.
consider some sort of non-local coupling in space, and numerically, like?
Numerically, you can get states very similar to these ones. That was the idea at first. We wanted to like recover these states without using the distance. You cannot. I mean, at least from my knowledge, I can say that you cannot get like Turing patterns. But if you make crazy things like adding chirality or something like that, you can get like very nice stuff. Yeah, like I don't know, like schooling or schooling type behavior. Yeah.
Okay, so thank you, João.
Good.
Next speaker is Pablo de Castro. He's going to continue on the same topic.